In this video, we will be recapping what you have learnt about orbitals at A level and linking this knowledge to topics learnt at the beginning of a chemistry degree.
An orbital is a region in space around the nucleus where electrons are likely to be, that can hold up to 2 electrons with opposite spins. Each s subshell contains one s orbital with a spherical shape. This can hold a maximum of 2 electrons. Each p subshell contains 3 p orbitals that each have a dumbbell shape. Because each orbital can hold up to 2 electrons, a p subshell holds a maximum of 6 electrons. There are also d and f subshells, which whilst may not have been focused on at A level and won't be highlighted in this video, they are important to note at degree level.
In a spin diagram, each box is representative of an orbital, with each orbital having a maximum capacity of 2 electrons with opposite spins. The s subshell contains one orbital, so its maximum capacity is 2 electrons, and the p subshell contains 3 orbitals with a maximum capacity of 6 electrons. The s subshell is lower in energy, so it is filled before the p subshell.
When atomic orbitals overlap, they can form sigma or pi bonds. Sigma bonds are formed from the direct orbital overlap of bonding atoms. Pi bonds form when p orbitals on 2 adjacent carbon atoms overlap. The pi bond forms 2 regions of electron density above and below the sigma bond. Notice how the pi bond is asymmetric about the internuclear axis, meaning if you were to draw a line connecting the 2 nuclei and rotate, you would be able to tell they had moved. Can you now explain the difference in symmetry between sigma and pi bonds?
These are the questions for the A-level recap segment of the video. The first question is, fill out the electron configuration for an oxygen atom. And remember to include the opposite spins on each of the arrows. Second is to draw an s orbital. The third is to draw a p orbital. See if you can have a go at drawing p orbitals with both pi and sigma overlap. Pause the video and write out your answers, and then press play when you're finished, and we will reveal the answers. Now we're going to go through the answers. So for question 1, you have to fill out the electron configuration for an oxygen atom. So of course, oxygen has 8 electrons in each atom. It's got 2 valence shells, and in the first valence shell, there's just one orbital, the 1s orbital. So we fill that up with 2 electrons, and make sure you've put in the opposite spins. Then for the second shell, we've got one 2s orbital, and 3 2p orbitals. So obviously the s orbital is lower energy than the p, so that gets filled with 2 electrons first. And then when we move on to the p orbitals, 2 electrons go into the first one, and then we have 2 electrons remaining. So if you've put both of these 2 into one p orbital, leaving one of the p orbitals empty, that is not correct, because both of the electrons are negatively charged. And so this means all of the electrons that are paired in an orbital are going to repel each other. And the system wants to decrease the overall energy. So if we put both of the electrons into 2 separate p orbitals, they don't experience this repulsion, and therefore the overall energy configuration is lower. So make sure you've got those last 2 electrons both in separate orbitals. Then for the second question, drawing an s orbital, this is a nice and simple question. It's just drawing a circle. And then for your p orbital, you should have a figure of 8 shape. And if you went on to do the overlap, pi overlap has 2 areas of overlap above and below the nucleus, and a sigma overlap is 1 area of overlap. And this is stronger because instead of being above and below the nucleus, it's actually overlapping with the nucleus. Once you've corrected your answers, move on to the next part of the video, where we'll start to introduce the degree content. If you got any of those questions wrong, feel free to go back and watch the first part again, and then try and do the questions again and see if you get the right answer this time.
2 atomic orbitals can come together to form a molecular orbital. Both sigma and pi atomic orbitals can form either bonding molecular orbitals when 2 like phases overlap, or anti-bonding molecular orbitals. when two different phases overlap. Here, we can see that the interaction between two s atomic orbitals in the same phase forms a sigma molecular orbital. The interaction between two s orbitals of different phases instead forms a sigma star antibonding molecular orbital, as seen here. P orbitals can form either sigma or pi molecular orbitals. When two p orbitals come together horizontally like this, with the same phases overlapping, they can form a sigma molecular orbital. Alternatively, if two different phases are next to each other, we can get a sigma star molecular orbital like we can see here. When p orbitals come together vertically, they form pi molecular orbitals. If the same phases are next to each other, a pi molecular orbital is formed. However, as we can see in this image, when two different phases are next to each other, a pi star orbital is formed instead.
These are the questions for the second part of the video, now that you've started to learn some of the degree level content. So the first question is to draw a sigma and a sigma star s orbital overlap. So remember, in the first part you learned how to draw an s orbital, and now you need to make sure that you can use what you've learned about the different phases and how those overlap to create a bonding and an anti-bonding orbital. As an extra challenge, try and label the nodal planes and the intermolecular axes. The second question is similar. Draw a sigma and a sigma star p orbital overlap. So again, remember what you learned earlier about the shape of the p orbital, and now you need to apply what we've just learnt with the different phases and the antibonding and the bonding orbitals. Then for the third question, draw a pi and a pi star p orbital overlap. Now remember, the difference between sigma and pi is that sigma is symmetrical around the internuclear axis and pi is asymmetrical about the internuclear axis. If any of that sounds a little challenging and you think you need to go back and watch the video again, feel free to do that before you attempt the questions. If not, pause the video and have a go, and press play when you're ready to reveal the answer. Now we're going to go through the answers. So for the first question, you have to draw a sigma and a sigma star s orbital overlap. Now remember, an s orbital is a circle, and we've learned that these orbitals have different phases. So, for a bonding overlap, you want to have two of the same phases. So we have two circles that aren't shaded in to represent two orbitals of the same phase, overlap to create a more sort of oblong shape with both the nucleus present there, and then we've got the internuclear axis drawn in. And you can see that this is symmetrical about the internuclear axis, and that's why this is sigma and not pi. Then for your sigma star overlap, of course, this is when we have two different phases to create an anti-bonding orbital. So to represent the different phases, we've got one circle shaded in and one circle not shaded in. And then you can see here, we've got a nodal plane. So there's an area of no electron density between those two orbitals of different phases. And this creates a sigma star, or an anti-bonding s overlap. Then, for question 2, we had to do the same thing. So again, a sigma overlap, but this is for p orbitals. So every p orbital has an end which has different phases. So we've got one end is not shaded and one end is shaded. The difference between the sigma and the sigma star is that in the sigma, the shaded ends overlap because obviously the shaded ends are both in the same phase. So if they both overlap, that creates a bonding orbital. This also has an internuclear axis that's symmetrical about, so that's why it's sigma. And then for the anti-bonding orbital, we have again the two p orbitals, except this time the phases are orientated so two different phases are facing each other. And then we have this shape here with another nodal plane, so this is an area of no electron density, and this is still symmetrical about the internuclear axis, so this is still a sigma overlap. But due to the different phases that are overlapping, it's a sigma star p overlap. So this creates an anti-bonding orbital. Then for question 3, this is where we start to see the difference between sigma and pi. So for the pi p overlap, we have again two p orbitals orientated so the same phases are going to be overlapping. So we've got the non-shaded side above the internuclear axis and the shaded side below the internuclear axis. So as you can see, this means it's not symmetrical about the internuclear axis. This is why it's a pi orbital, and the same phases are overlapping. So this is why it's not a pi star, it's just a pi overlap. And then for the pi star overlap, we have different phases overlapping to create this shape, which again is not symmetrical about the internuclear axis. So it's again a pi overlap, and because of the different phases, it's a pi star overlap, and this creates an anti-bonding orbital. Now, these questions were a lot more complicated than ones in the first part, so if you need to revise the theory, again, if you've got any of those questions wrong or you're still confused, feel free to refresh the video, watch that part again. If you got all those questions right and you're confident, then feel free to press play and move on to how to draw a molecular orbital diagram.
This is a molecular orbital diagram for a H2 molecule. This molecule consists of two hydrogen atoms, each consisting of one atomic orbital. These are represented by HA and HB. Hydrogen only has one valence electron in the 1s orbital, as shown by the diagram. Below the atomic orbitals in the diagram is the bonding molecular orbital, as it is lower in energy, and above is the anti-bonding because it is higher in energy. These are represented by sigma and sigma star. One electron is drawn in each of the atomic orbitals. This represents the individual hydrogen atoms. The electrons are then filled into the molecular orbitals, starting with the lowest energy orbital, which in this case is the 1s bonding MO. Both electrons are placed in this molecular orbital, so there are none in the anti-bonding MO.
The formula for bond order is the number of electrons in bonding orbitals subtract the number of electrons in antibonding orbitals, all divided by 2. A bond order of 1 is a single bond, 2 a double bond, and 3 a triple bond. Paramagnetism is the presence of unpaired electrons, while diamagnetism means that all electrons are paired.
Now that you've learned how to draw a molecular orbital diagram, it's your turn to have a go. So pause the video and try and draw a molecular orbital diagram for diatomic lithium. If you get stuck, press play to watch the explanation, or go back and watch the H2 example again, and then have a go for diatomic lithium. Okay, so this is the explanation of how to draw a molecular orbital diagram for lithium. First of all, I'm going to go through the basic framework here. So, you can see on this side we've got one of the lithium atoms, this side we've got the other. Now of course these are both the exact same atom, so both these sides of the molecular orbital diagram will be exactly the same energies. So we have the 1s orbital for lithium and the 2s orbital for lithium. We don't have any p orbitals in lithium, so we don't have to worry about that. Then for the other lithium atom is exactly the same, the 1s and the 2s. Now we have to worry about the overlap that we learned in the second part of this video. So the 1s, you're going to have a sigma 1s overlap, and you're also going to have a sigma star 1s overlap. So remember, the sigma star overlap are higher in energy than the sigma overlap. So this means that we put them higher up on the diagram. The sigma 1s orbitals are lower in energy than the 1s, so we put these lower. Sigma star higher, so we put these higher. And the sigma star are higher by a larger amount than the sigma are lower. So if you can see here, the dotted line going up to sigma star is slightly longer than the dotted line going down to the sigma. And it's the exact same concept for the 2s. So we've got sigma 2s lower in energy than the 2s. The sigma star 2s is higher in energy, and it's also further up than this is down. The dotted line is slightly higher going up than that one is. Right, so now it's time to fill in our electrons. Okay, so now I filled in the electrons here in red. So up here we've got the lithium electron configuration, and we can use this to help us with the first section. So initially just ignore this middle section and just focus on each atom of lithium on either side here. So of course we've got 2 electrons in the 1s, which we've also got down here and here for each of the lithium atoms. And then we've also got 1 electron in the 2s, which we've got here and here. So essentially these 2 sides are just representing this, but in a different format. So we've got both of our lithiums here and here. And then when they combine to form diatomic lithium, obviously you've learned about the orbital overlap. So first of all, at our lowest energy configuration, we've got the overlap of the 2 1s orbitals to create the sigma 1s orbital. And then slightly higher in energy, we've got the sigma star 1s, so that is the anti-bonding orbital. So what we had when 2 s orbitals of different phases overlapped. And as you can see here, the sigma star, so that anti-bonding orbital, is higher in energy than the sigma or bonding orbital. And if you can see, the dotted line going up to that is longer than the dotted line going down here. And that's to represent that the difference in energy between these 2 orbitals, so the 1s and the sigma star, is greater than the difference between the 1s and the sigma 1s. We have a similar concept for the 2s. So we've got our bonding orbital, where orbitals of the same phase overlap for the sigma 2s. Of course, the 2s is higher in energy than all of the 1s. And then again, we've got the anti-bonding orbital here, so the sigma star 2s orbital. And again, this is a longer dotted line up here, because the difference in energy here is greater than the difference in energy here. Right, so now we're going to fill in our electrons. So we've got 4 1s electrons in total. So first of all, we fill the lowest energy with 2 electrons in the sigma 1s, and then we move up for the remaining 2 electrons. We put them in the sigma star 1s. Then we move up to the next energy orbital. We've only got 1 electron in each of these 2s, so we've got both of those in the sigma 2s, because we don't want to have one up here, because then that's going to make the energy a lot higher than it needs to be. So we're just going to put both of them down here, and that keeps the energy overall lower. So of course the sigma star 2s orbital, or the anti-bonding 2s orbital, remains empty. And that's all of it. If you found any of that confusing, or you didn't manage to get that, go back and watch the explanation for the hydrogen one again, and then have another go. If you've completely grasped that concept, then you can even go on to try and draw another molecular orbital diagram for a diatomic compound that has more than just 3 electrons in it. But for everything we're going to go through the video today, that's all.